Very good day to be here. My name is S.Adebayo. We want to continue from where we stopped on our last class, and we have week 3 of our classes now. We shall be discussing electrochemical cells today. And under this, we are going to be talking about the standard electrode potential. We talk about how do we draw cells and how do we write cell notation. We talk about the EMF of cells and what are the applications of the electrochemical cells. Electrochemical cell is a device that converts chemical energy to electrical energy. That is exactly what happens in most of the cells. It might be the battery of a car. It might be the normal battery of your wristwatch, remotes. It might be the battery of your work clock or just your phone, whatever cell, because they are cells. The electrochemical cells is a device that converts chemical energy. There is a presence of chemical energy because all these things, all these device contains chemical inside of them. So they contain chemical energy to electrical energy, and they are being used to supply energy. So what we want to really talk about some parameters that are associated with the electrochemical cell. The first parameter is what we call standard hydrogen electrode. The standard hydrogen electrode consists of hydrogen gas at 25 degrees centigrade, that is a room temperature, and 1 atmospheric pressure bubbling around an inert platinum electrode in contact with 1 molar solution of hydrogen ions. And look at that, we have H plus aqueous, we have H2 gas system. So the hydrogen electrode or standard hydrogen electrode is the reference standard by which the standard electrode potential of any metal is measured against. So the standard hydrogen electrode or standard hydrogen electrode potential has been given or has been assigned a value of 0. So the standard hydrogen electrode for any substance is originally or typically assigned to be 0. It is assigned to be 0. Okay. The standard electrode potential. Don't forget all this, we shall be clearer when we start using them. We have standard hydrogen electrode. I told you that is the electrode that consists of hydrogen gas at 25 degrees centigrade and 1 atmospheric pressure, bubbling around platinum electrode in contact with 1 mole. And standard electrode potential, that is E naught. Standard electrode potential of a metal, that is of a metal or ions, is the potential difference set up between a metal and 1 molar solution of its ion at 25 degrees centigrade. And arbitrarily taking the standard electrode potential of hydrogen ions or hydrogen gas to be 0 volts. So the standard electrode potential is talking about the potential difference. So that is being set up between the metal and 1 molar solution of the ions at a room temperature. But the standard hydrogen electrode is the hydrogen gas, is the it's hydrogen gas at 1 atmospheric pressure and at room temperature that is around the platinum electrode. Now, the third thing I want to talk about here is salt bridge. The salt bridge is a piece of paper soaked in potassium chloride solution or ammonium chloride solution. And what does it do? It functions is to complete the electric circuit and enable the movement of ions from one half cell to another so as to maintain electrical neutrality in the solution. This salt bridge is a kind of interface, a kind of what do we call it? A kind of material that is being dipped, that is being soaked inside ammonium chloride or potassium chloride to complete the circuit so that electrons can flow from half to another half of the circuit. How do we measure the standard electrode potential? The standard electrode potential of a particular metal, which is the half cell of the metal, its system. Look at it. I want to also at least start working now. We have Zn 2 plus aqueous here. That's the way we write the standard electrode potential for zinc. And we then have zinc solid to the so slash the zinc solid. Now, in measuring the standard electric potential of a particular metal or ion, the half cell of the metal system is connected to that of hydrogen gas system by a salt bridge. So a salt bridge is one that will be in between the half cell of that metal with that of hydrogen. You know, the hydrogen is what, as I said, the standard hydrogen electrode is used as a standard here. We now connect it to the standard electrode potential of the particular metal. Here, in this case, is zinc. The reading shown on the voltmeter. You know, we now connect the voltmeter. The reading shown on the voltmeter shows the electromotive force, which is the EMF of the cell. So since the standard electric potential of the hydrogen ions or hydrogen gas system is assigned to be zero at the original position, the value obtained in the standard electric potential of the metal system. By the time you look at the example, you understand this. The sign of the standard electric potential of a given metal system is dependent on the direction of the electron flow in the cell. The sign of the standard electric potential of a given metal is dependent, that is, does not depend on the direction of electron flow in the system. If electron flow from hydrogen ions or hydrogen gas system to metal, the standard electric potential of that metal is assigned to be negative. It flows from hydrogen. When it flows from hydrogen to the metal, the standard electric potential is negative, and if it flows from the electron in the reverse, if it flows from the metal to the hydrogen ions, it is assigned to be positive. That's in reverse. So for example, the standard electrode potential of zinc ions or zinc metal system is minus 0.76. This is just because during the measurement, the flow of electrons is from the hydrogen system to the zinc. The flow of electrons is from hydrogen system to the zinc. So that's what we are being given. What we are being given is just the E naught, and I have explained what E naught means. E naught is the EMF that cut across. So this is when we have zinc from the zinc ions to zinc metal. We have, this is the voltage, and from copper ions to copper metal, and then we have the 0 plus 0.3. So when we have a positive, it actually means the electron flow in a reverse direction. That is, it flows. You know, I told you that it is a negative if the flow is from the metal to the hydrogen ions. I told you if the electron flow from the hydrogen ions system to the metal, rather, it is negative. And when the electron flow from the metal to the hydrogen ions, it is positive in nature. So that is the reason for the signs you are seeing there. This is a typical example of a cell. This is a typical example of a cell. You can see there is anode, there is a cathode. We shall talk more about this under electrolysis. We shall talk more about this under electrolysis. This is a typical example of a cell. So, excuse me, I think I need to off this for now. I need to put this on airflow play mode. Sorry. Okay. Now, let's continue. Let me talk about what happened in this cell, which I just show you. Let's talk about what happened here. Okay, we have a cathode, we have an anode. A cathode, because it is an anode, which is a negative electrode. That means we have two electrodes. We have a cathode, which is a positive, you can see the sign, positive electrode. Okay, and look at this. This is a salt bridge that we used to connect. You can say I told you what a salt bridge what it does rather in the last stuff. So it's the one that allows the current to flow from both anode from the two electrodes rather. The same thing, we have a salt bridge here, which is the one that connects the whole flow and allow current to flow. Now let's discuss it. Then I will be referring to this diagram. When two half cells with different electrode potential are connected through a salt bridge, they form a cell called electrochemical cell. That is what we have here. This is half cell. This is another half cell. They are being connected with a salt bridge. What we have here is electrochemical cell. The same thing. This is a half cell. This is another half cell connected with a salt bridge. What we have is the electrochemical cell. Okay. Now, the electrochemical cell is also called a voltaic or galvanic cell. And it is the device in which chemical energy is converted to electrical energy. I told you that what a cell does mainly is to convert chemical energy to electrical energy. In this, the electrochemical cell, oxidation occurs in one half cell, while reduction occurs in the other half cell. Mainly, a electrochemical cell work on the principle of oxidation and reduction that we just discussed. Okay. The overall redox reaction results in flow of electrons or electric current. For example, if the zinc aqueous zinc ion to zinc metal half cell is connected to zinc ion to zinc metal half cell through a salt bridge with the copper ion copper solid made the right hand electrode, the cell produced is called a Daniel cell. In this cell, oxidation occurs at zinc electrode. Oxidation occurs at zinc electrode, and the electrode is then negative of the anode. Reduction occurs at the copper electrode, which functions as positive electrode or cathode, as shown in the figure. Now, this is exactly what we are talking about. So, if you look at this now, oxidation occur here. You can see the formula here, and reduction occur at here. I think, as I said here, I said oxidation occur at zinc electrode, and that's exactly this is where the oxidation occur. This is where the reduction occur. Look at the equation. The equation here will show you if you really understand the oxidation reaction, and this is the whole complete redox reaction that is being balanced. This is the whole complete redox reaction, and this example is a Daniel cell. Okay. And that's exactly, I think I showed this under this diagram. Now I want us to quickly go to cell notation. How do we write the cell notation? In the cell notation above, the single represent phase boundary between the metal ion, that is the single line, and the metal electrode, while the double line represent the salt bridge. Now, this single line, it actually means the single line slash. It means phase boundary between the first, we have zinc solid to zinc ion, we have copper ion to copper electrode. This is like a boundary. So, but this actually means the salt bridge. The double line means the salt bridge that is in between the two of them. So we said that oxidation occurs at the zinc. Look at now, we can say that is addition of zinc is from 0 to this one is 2 now. You can see that is oxidation. Addition, the gaining of the more charges. And when we have more charges, that is oxidation. When we have lots of charges, we have reduction. You can see zinc here. Zinc is 0 at the free state, but zinc 2 plus is 2, the oxidation number. So you can see that increase in oxidation number. That's oxidation. So oxidation occur at that zinc area. Now look at reduction. Copper before having 2, but now copper to is now having 0. So reduction occurs at that. So when we now write the main reaction, zinc, that is the zinc 2 plus gaining 2, we have oxygen reaction, that is the, and we have copper, we have copper losing 2 electrons here, and that is reduction reaction. Ions is formed, you can see in the oxidation. So ions can be defined as element which has either gained or lost electron. EMF of a cell. I told you that E naught is used to represent EMF of a cell in an application, in an electrochemical series. And let's look at the application. The EMF of this electrochemical cell is algebraic difference between the standard electrode potential of the two metallic electrodes that are being used. So the EMF is EMF of the cathode, that is the one that is used as the positive electrode, and minus EMF of the anode, the one that is used as negative. So a big EMF means powerful cell. If we need a powerful cell, the metals which serve as electrode should be far apart. Now, that's not even our main concern here. A positive EMF, the sign, we said that the sign of the EMF tells the reaction in the cell is spontaneous. That is exactly. Or tell whether the reaction is spontaneous or not. So a positive means, when we say positive, it means it is spontaneous. And when you have a negative EMF, it is not spontaneous. That's exactly what I want to understand there. So now the relationship between EMF and delta G. Don't forget delta G, that is the spontaneous reaction, is that delta G equals to minus N, that is number of moles of an electron, F, the Faraday constant E. Delta G is minus NFE. That's the reaction between a delta G, which is the spontaneous reaction, and the Faraday constant with number of moles. The E actually represents the EMF. Okay. Now, let's look at this together as an example. Find the EMF and delta G of the cell represented by half-cell equation. Look at this. We are given, this is the EMF of the copper given here, and this is the EMF of the silver. Now, don't forget that we said that EMF is the EMF of the cathode minus EMF of the anode. And if you look at that, the cathode here is the silver. This is the silver because this is the one that is losing. You know, this is what we call reduction. Reduction takes place at the cathode, and the oxidation takes place at the anode. So this is exactly reduction. You can see from Ag plus Ag at 0. So the EMF, according to the formula I wrote, the EMF is EMF of the cathode minus EMF of the anode. And they give us EMF of the cathode to be 0.80 and the EMF of the anode is 0.340. So when we subtract, you have this one. So that is the EMF. That's first thing. When we get the EMF, let's now get the delta G. Delta G is minus NFE. Don't forget. The Avogadro constant is 96,500. That is the F. That is Avogadro's constant. That is 96,500. That is the constant. And don't forget, we have gotten our EMF to be 0.46. But we say minus N, number of moles. If they look at this, the number of moles here is 2. Number of moles here is 2. So we have 2 by, that is minus 2. This is supposed to have minus 2 by 96,500 times 0.46. And we get minus 88. The 780. We can judge whether that reaction is spontaneous or not, but with that expression. So if it is positive, it means the reaction is the cell spontaneous, and it's so that such cell can work otherwise. So can work. So otherwise it's not workable. So whenever it is negative, it means that such cell is not workable. So that's exactly you can meet the application of electrochemical cell. Examples of electrochemical cells are Daniel, Leclanche, lead acid accumulator, that is the car battery. These cells are used in power generation. What are the applications? We have a primary cells and the secondary cell. The primary cells are the cells that are rechargeable, while the secondary cells are the cells that are not rechargeable. So the primary cells are rechargeable because both reactions in the cells are irreversible. So the reaction in the cathode and you can reverse them. So only they are discharged, they cannot be used again. They are irreversible. So whenever we have the primary cell, the reaction cannot be reversed. They are irreversible. But in the secondary cell, the reaction is reversible. So that is why when you use, so there are some batteries or cells, when you use them, you can't use them again. It is spoiled. But there's some batteries, when you use them, you can still charge them and still use them. That is the secondary cell because the reaction in this half cell can be reversed. So the chemical reaction in these cells are reversible. That is for secondary cell, and that is why they can be recharged after use. Example of the cell is car battery, some handset battery, laptops battery. All those ones are secondary cell because we can recharge them. But the ones that we use in our remote, in our work clock, this watch are most not rechargeable because the reaction are not reversible. They are irreversible. An example of that is Daniel and Lakeland cell. These are practice questions that you need to work upon before our next class. Because our next class we are going to talk about the electrolysis. How do we perform electrolysis in the laboratory, and what are the basic calculations that are under electrolysis. This aspect is just to show you an idea to what we are going to be doing about electrolysis. Don't forget, you need to subscribe and try to on the bell in our YouTube channel so that you can keep on seeing videos that we are dropping for you. Thank you very much and have a blessed day. Now, this is the later part of the questions too.